Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning. And this video is about the topic of recursive neural networks. And that is topic number 9 in the list of topics which are covered in this course. And this topic is further divided into lecture 9A, which means that we look at the basics of the concepts of recursive neural networks. Very basics. That's why it's 9A. And this video is developed using the supplemental website, which is accessible at www.ezmcq.com/goget, which is a personalized learning management system. So, what is the future of content delivery? That is not the future alone, that is also the present, because there are literally hundreds and millions of end users who are getting educated using the content delivery platform and mechanism, which are in hundreds and millions. So that is the approach which is being used in delivering and explaining the concepts in this course. So the personalized learning management system is accessible using the URL which is given in green color, and the content delivery mechanism is explained using 6 videos, and those videos are accessible using the link given in blue color. So what are those features which I've mentioned? These features consist of advanced and basic content search, which is not there in leading learning management systems. And then, of course, the ability to support people with visual disability, such as changing the font size, color, line spacing, and so on. And then this content is organized in such a way that it can efficiently use the limited speed, the limited space, and the speed of a handheld device. And of course, you can track your progress, what you have seen, done, and what you need to do. And then, of course, you also can test yourself online in real time, your knowledge assimilation and knowledge capturing. So, how the content is delivered? The content delivery can be question and answer based, and it can be traditional slides based. Now, the question and answer based approach is engaging, is proactive, it promotes thinking, and of course, it is very productive also. And the traditional approach contains a lot of details. So, the approach we have been following in this course is a blended approach, which is the best of both. So, these are the topics which are covered in this course, and the topic which is being covered in this video lecture is recursive neural networks. And these are the details of those question and answers, which are basically the concepts. So one set is shown in yellow color, and the other set or video is in green color. So now we move on to the details of that course. So this is topic 9A of deep learning. So we click on deep reinforcement learning, and here is the table of contents. And from the table of contents, we will click on the 9th topic, which is recursive neural networks. So we click on it. So we have been talking about, we have discussed, we know about recurrent neural networks and recursive neural networks also. So which is the topic for this lecture, recursive neural networks. So the question which immediately comes to our mind is, what are the fundamental differences between recurrent neural networks and recursive neural networks? So there are quite a few differences in terms of data structure and network flow and so on, which are in front of you. So as you can see that for recurrent neural networks, which we have already covered, so we unfold the neural net in time. So we unfold it in time. So these are the inputs, X are the inputs and Y's are the output, and these instances are at different instances of time. Okay. Now, if you look at recursive neural networks, so there's a hierarchy over here. So we have this statement, for example, that movie was cool. So we have a tree here, and that tree structure is which is used to implement or represent the recursive neural network. So coming back to the background, in summary, RNNs, okay, which is the notation for recursive, which is notation for recurrent neural networks, and RvNNs, which is the notation we are using for recursive neural networks, they fundamentally differ in their domain of application. right? And their difference in the architectural flow, their difference in dependency modeling, and the way the training takes place. Now, recurrent neural networks, RRNs, handle temporal sequences in time with information flowing along the time steps at time t, t minus 1, or t plus 1, and so on. Okay. All right. So, and they are prevalent in these RNNs are prevalent in reinforcement learning and while doing sequential tasks. But recurrent neural networks have that domain, but recursive operate in a hierarchical structure, which is in front of you also. And they merge the child nodes into parent representations and so on. So these are suitable for parsing and compositional semantics. Now, input dependencies in RNNs are linear over time. While you can see that the recursive neural networks, they mirror structural relationships, they mirror hierarchies over here. So training RNNs uses backpropagation over time, unrolled chains, while training recursive neural networks uses structure-aware backpropagation over variable tree depths. So this depth can be different. Now, because of branching and irregular architecture, recursive neural nets often incur greater training complexity. Because this is a linear structure. This is highly nonlinear, and you cannot say anything in advance about the depth. So choosing between them for the same problem depends upon whether your problem is fundamentally sequential or your problem is fundamentally structural. So these are the details in which we will dive into, and we start with them now. So starting with the data structure. So recurrent neural networks process sequences or ordered list of observations over time. Therefore, their structure is linear in time. However, contrastingly, recursive neural nets process hierarchical or tree structured inputs, as you have seen and I've shown you, like phases or and so on. So, recursive neural nets take advantage of nested and compositional structures, and which are input by combining subparts into larger. So, you combine subparts into a larger representation, then we combine them into further larger representations and so on. Okay, so now in terms of network flow, recurrent neural nets information flows through time steps. Okay, and each hidden state carries the context forward. In recursive neural nets, flow is not linear, flow is structural. Child nodes are merged upward into parent nodes, and those parents which are the child of some other nodes, they are merged together and so on until we reach the root. Now, this flow reflects either temporal recurrence or compositional structure. So it is up to you and up to us that how we proceed with them and which one we select to use or opt to use. So what are the applications? Now, recurrent neural nets are commonly used in language, speech, time series, inherently time series, and reinforcement learning tasks involving sequences. Now, recursive neural nets are suited to structure tasks like parsing, sentiment composition over syntactic trees, or naturally representing hierarchical data, where input has a tree-like structure, it is like a logical tree-like structure, not really a literal tree, but a logical tree-like structure. So what about the input dependencies? Now, input dependencies in recurrent neural nets, I'm repeating something which is actually should be repeated. There is a temporal order. In recurrent nets, there is a temporal order. Earlier inputs influence later predictions, and how that's done through the hidden states, because that's not non-Markovian. Now, in recursive neural nets, dependencies follow structure. Child node values affect their parent node, and those parent node which are child of other and so on, they reflect beyond. So the nature of the dependency graph differs, right? As you can see here, the graph here is linear like a chain. The graph here is a tree, okay? And of course, linear versus branching. And then is what about the training complexity? The training complexity, recurrent neural nets are trained with back propagation across time. Now, so it's linear. So complexity is proportional to sequence length. As opposed to uh, recursive neural nets, they use back propagation over the space, over tree structure. So the complexity depends on the tree shapes. The complexity depends upon the branching, the merging, and this tree I've shown you. It can be highly irregular also. So therefore, a batch processing and parallelization of recursive neural nets is more challenging. So we move on to the next Q&A or the next concept. All right. So when it's more appropriate to use a recurrent neural net versus recursive neural net? That's a very interesting question. So these are the domains, or when to use recursive and when to use recurrent. So it depends upon the hierarchical structure of the modeling, how you can better compose the problem, and how it is easy, how much it's easy and difficult to interpret the improvement. Okay. So before we go into this comparison, so let me spend some time on the background. So in deep reinforcement learning, the choice between recurrent neural net over recursive neural net is suitable when the domain lacks the strongly nested hierarchical input structure. Then we go for RNN. When compositionality is temporal rather than structural and interpretability is simpler and optimization are prioritized, then we again go for recursive. No, but we go for recurrent neural nets. So recurrent neural nets are more efficient. They're easier to train using backpropagation. They are less reliant on structural annotations, and they're often, not always, often sufficient for problems centered on time-dependent inputs like sequences of observations and actions. While recursive neural nets, okay, they are a good choice when hierarchy is inherent. So there's inherent hierarchy, like in a sentence, and that hierarchy must be exploited. For example, parsing, for example, scene graphs, which is an example towards the end of this part. So recurrent neural nets remain a robust and flexible choice for many deep reinforcement learning tasks. Now, optimization techniques like gradient handling or memory or computational cost are also in the favor of recurrent neural networks. So, what are those conditions? These conditions are in front of you. So, why we would use hierarchical structure? Okay. So when we will use RNNs, recurrent neural nets, use them when your data does not have or require explicit hierarchical structure. Then use recurrent neural nets. Now, if the state or input is flat, it's linear, temporal, or already summarized, then what's the point in adding recursion? Because it just adds overhead and unnecessary complexity. So we are looking at the first point here. In deep reinforcement learning, many environments produce sequences of observations rather than nested compositional structures. Now, without a reliable parse or hierarchical decomposition, recurrent neural nets are simpler, they are faster, and they are less error prone for modeling these temporal dependencies. So this is how it's suited. Now, better compositionality. What does it mean? When the composition in your task is mainly about combining the past temporal context, observations, or rewards or actions. Now, remember, reward is something which is specific to reinforcement learning. Now, rather than instead of these, it is like composing the nested subcomponents like phrases, sub objects. Okay, then recurrent neural networks are not the ideal, but they suffice. Now, recurrent nets naturally handle temporal composition with hidden state carrying forward. And for tasks like sequence forecasting or policy learning over time, policy learning is again from reinforcement learning. Recurrent nets offer strong compositionality over time without needing any structural merges, which are the merging the leaves for the parent and so on in recursive neural nets. So only when the data includes meaningful sub subcomponent composition, subcomponent. like text parse or object hierarchy, then we use recursive neural nets. Then the recursive neural nets becomes more important. And finally is the improved interpretability. Now the step-by-step evolution of recurrent nets, hidden states, gives more direct visibility and understanding and comprehension of how each past input influences the decisions. Now debugging sequence dependencies, checking which time steps contribute, is more straightforward. However, as with contrast to recursive neural nets, they require examining a tree structure, child node merges, and there is a structural variability also because it is not non-linear. Linked recurrent are totally linear. So there is a structural variability in recursive neural nets, which obviously adds complexity. So when explainability, debugging, or transparency are important, okay, and they are simpler and more uniform, then we go for recurrent neural networks. They are more preferable. All right. So here here are more details. Here are more comparisons. So we see that, for example, when we need visual scene understanding, visual because the scene has a hierarchy, then we go for recursive neural nets. But when it's like text generation or machine stock prediction, which is totally temporal, then we go for recurrent neural nets, and so on. So interpretability, low interpretability, hidden states are not directly explainable. High interpretability, each node has a semantic role. So it depends upon the application, it depends upon the domain. So these are like 7 or 8 different aspects on which the comparison has been made. So now we move to the next Q&A, which is what types of data structures are best suited for recursive neural nets. All right. So obviously that's a tree structure, but let me spend some time and go over. So obviously it's a tree structure, okay, and we can have tree structures in graphs and parse trees graphs. You know that every graph is not a tree, but every tree is a graph. So one has to be careful about this. So for the background, recursive neural networks are best suited for structured hierarchical data that we have discussed as opposed to flat sequences. Now the ideal data structure for recursive neural nets includes trees, graphs, particularly DAGs, directed acyclic graphs, and parse trees. Now, of course, which one is better depends upon the domain. Now, trees provide natural nested structure, which enables clean bottom-up recursion, okay, which we cover in data structures. So, graphs generalize trees to more flexible connectivity, suitable when multiple parent-child relationships exist or shared substructures exist, meaning that the loops are there. So, these are not trees, but they are graphs. Because as you know, trees don't have loops. So parse trees, especially in NLP, natural language processing, are a specific or canonical application of recursive neural nets. Why? Because they capture the syntactic compositional structure to build the embeddings for phrases and sentences. So that is all covered in the natural language processing course, which is also available on if you go easymcq.com/NLP. So the choice of the appropriate data structure for the recursive neural net depends or aligns with the topology of the recursive model. It has to align with your domain inherent relationships. And whichever the choice is enabling better function composition, gradient propagation, and the representational expressivity, where in tasks where hierarchical abstraction matters. So you see that a sentence consists of a noun phrase and a verb phrase. Then the verb phrase has a verb and a noun phrase. So you see that Homer hit Bart. So these are the leaves, and we combine them into parents and combine them, and we end up in a sentence. So there's a natural hierarchy. So if you go into more detail, so that with reference to the tree structure, so classic hierarchical structure where nodes have children but no cycles. So the example which I've shown you has no cycle. So recursive neural nets recursively compute node representations bottom up, and how it is done using composition functions. Now, the trees match the domains like scene decomposition, which we will cover, syntax, and enable stable optimization. How? Through structured recursion. All right. And then are the graphs. More flexible than trees because the graphs allow arbitrary node connectivity, which creates cycles, and multiple parent relations, which create cycles. Okay. But the thing is that we are not talking of generic graphs. We are talking of directed acyclic graphs. So this is fine as long as the cycles are avoided. We are not talking of undirected graphs. So recursive neural nets over graphs or DAGs aggregate neighbor or child embeddings recursively. What it does, it enables richer structural modeling in and of course where in molecules, in knowledge graphs, or for relational domains. So these are domains where they work well, and with the domains which have a natural hierarchy. And then the parse trees. Now parse trees are specialized structures which represent sentence syntax. So they are widely used in NLP, natural language processing. They are widely used. So parse trees guide the recursive neural nets to produce what is called as compositional phrase or sentence embedding. So this is from the domain of natural language processing. There's a whole course on it available at easymcq.com/NLP. The structured nature makes training, recursion, and embedding composition more interpretable and linguistically well understandable. So this is the beauty of that specific data structure.